The universe is full of wonders. We have sparkling stars, swirling galaxies, and planets of all shapes and sizes, but among all these cosmic treasures, there is nothing quite as strange or as powerful as a black hole. Imagine a spot in space where gravity is so incredibly strong that nothing, absolutely nothing, can escape its grip. Not a spaceship, not a planet, not even a beam of light, which is the fastest thing in the entire universe. That is what a black hole is. It's like the universe's ultimate trapdoor, a one-way trip to a destination we can only imagine. These objects are not empty holes. They are packed with an enormous amount of matter squeezed into an impossibly tiny space. So, why are they called black holes? It's because they are truly, perfectly black. Since light cannot escape from them, they don't shine or reflect anything. They are invisible against the dark backdrop of space. We can't see them directly with our telescopes in the same way we see a bright star or a glowing nebula. Instead, scientists have to be cosmic detectives. They look for the clues that a black hole leaves behind. They watch as stars get pulled and stretched, swirling around a dark, unseen center. It's like trying to find a person in the dark by watching how they knock over furniture. The chaos they create tells us they are there. This immense gravitational pull comes from something called density. Think about it like this. Imagine you have a big, fluffy pillow. It's large, but not very heavy. Now imagine you could squeeze that entire pillow down until it was the size of a tiny marble. It would still have all the same stuff in it, but it would be incredibly dense and heavy for its size. A black hole is the most extreme version of this idea. It takes the mass of a giant star, many times bigger than our own sun, and crushes it down into a point smaller than a single atom. This super dense point creates the mind-bending gravity that defines a black hole. Because of this, black holes are one of the greatest mysteries we are trying to solve. They challenge everything we think we know about the universe, about space, and about time itself. They are cosmic laboratories where the rules of physics are pushed to their absolute limits. When we study them, we are not just looking at a weird object in space, we are peering into the very fabric of reality. We are asking the biggest questions. Where did the universe come from? What are the fundamental laws that govern everything? And black holes, these silent, dark giants, might just hold some of the answers we are searching for. So where did these incredible cosmic monsters come from? They aren't just born out of nowhere. The recipe for a black hole begins with one of the most beautiful things in the cosmos, a giant star. We're not talking about a star like our sun. We need a star that is truly massive, at least 20 times more massive than our sun. These giant stars live fast and die young. For millions of years they burn with incredible brightness, fusing elements in their core and shining across the galaxy. This burning process creates a constant outward push, like a giant explosion held in check, which battles against the star's own powerful gravity, pulling everything inward. This cosmic battle between the outward push of fusion and the inward pull of gravity can only last for so long. Eventually, after millions of years, the giant star starts to run out of fuel. The fires in its core begin to sputter and die down. When this happens, the outward push weakens, and gravity, the relentless inward force, finally wins the fight. The star's core, which is already incredibly dense, can no longer support its own weight. In a fraction of a second, the entire core collapses in on itself under the crushing force of its own gravity. This collapse is so violent and so fast that it triggers a spectacular explosion. This explosion is called a supernova. It is one of the most energetic events in the universe, an explosion so bright it can outshine an entire galaxy for a few weeks. The outer layers of the star are blasted out into space, seeding the cosmos with heavy elements like gold and silver. But what about the core that collapsed? If the original star was massive enough, nothing can stop its collapse. Gravity is now completely in charge, and it squeezes the core smaller and smaller and smaller. It crushes it past the point of being a solid, a liquid, or a gas, into a state of matter we don't even have a name for. The core continues to shrink until it becomes what scientists call a singularity. This is a point of infinite density, a place where all the mass of the star's core has been squeezed into a space with zero volume. It's a concept that breaks our everyday understanding of physics. This tiny, unbelievably massive singularity is the heart of the new black hole. Its gravity is now so immense that it warps the space around it, creating the dark, inescapable object we have come to know. From the fiery death of a magnificent star, a new and mysterious cosmic object is born, ready to begin its silent reign. Every black hole is surrounded by an invisible boundary, a line of no return. Scientists call this the event horizon. You can think of it like the edge of a giant cosmic waterfall. Imagine you are in a canoe paddling on a river that leads to this waterfall. At first, the water is calm, and you can easily paddle away. But as you get closer to the edge, the current gets stronger and stronger. There comes a point where the water is flowing so fast that no matter how hard you paddle, you can't escape. You are going over the edge. The event horizon is just like that point for a black hole. Once you cross the event horizon, there is no turning back. The pull of gravity becomes so powerful that you would need to travel faster than the speed of light to escape. And as far as we know, nothing in the universe can travel faster than light. So, once something, a star, a planet, or even a beam of light, crosses that boundary, it is trapped forever. It is pulled deeper and deeper into the black hole, toward the singularity at its center. The event horizon isn't a physical wall you would bump into, it's simply the point in space where the gravitational pull becomes unstoppable. From a safe distance, if you were watching a friend in a spaceship travel toward a black hole, you would see something truly strange. As your friend got closer and closer to the event horizon, their spaceship would appear to slow down. It would look like they were moving in slow motion. The light from their ship would become redder and dimmer. As they reached the event horizon, they would seem to freeze in time, stuck at the edge forever, until they eventually faded from view completely. You would never actually see them cross over into the black hole. But for your friend inside the spaceship, their experience would be completely different. They wouldn't feel themselves slowing down or freezing at all. For them, time would seem to be passing normally as they sailed smoothly across the event horizon. They wouldn't even notice the exact moment they crossed the line of no return. Once inside, however, they would be on a one-way journey toward the center. The powerful gravity would stretch everything out like spaghetti in a process scientists call spaghettification. The journey ends at the singularity, a place where our understanding of space and time completely breaks down. Albert Einstein gave us a revolutionary idea about the universe. He said that space and time are not separate things but are woven together into a single fabric called space-time. You can imagine this fabric as a giant, stretchy trampoline. Massive objects like stars and planets create dips or curves in this fabric. This curvature of space-time is what we feel as gravity. A planet orbits the sun not because it's being pulled by an invisible rope, but because it's following the curve in space-time created by the sun's mass, like a marble rolling around a bowling ball placed on the trampoline. Now imagine what a black hole does to this trampoline. It's not just a small dip like the sun creates. A black hole, with its immense mass packed into a tiny point, creates a deep, bottomless pit in the fabric of space-time. The curve is so steep that it basically becomes a vertical drop. This extreme warping of space-time is what causes all the strange effects we see near a black hole. It's like a funhouse mirror for the universe, twisting and distorting the very rules of reality. Time and space are no longer the steady, reliable things we experience here on Earth. This is why time behaves so strangely near a black hole. The deeper you go into a gravitational field, the slower time passes. This effect is called time dilation. Even on Earth, time passes ever so slightly slower for someone on the ground than for someone in an airplane high above, because they are closer to Earth's center of gravity. Near a black hole, this effect is magnified to an incredible degree. If you could orbit a black hole for a few hours and then return to Earth, you might find that decades or even centuries have passed for everyone back home. The black hole's gravity literally slows down the flow of time. This incredible power to bend space and slow time makes black holes one of the most fascinating subjects for scientists. They are the ultimate testing ground for our theories about gravity and the universe. By studying how light and matter behave at the edge of a black hole, we can learn more about Einstein's theories and maybe even find new physics that goes beyond them. Black holes are not just cosmic destroyers, they are cosmic teachers. They hold the secrets to the fundamental nature of space, time, and gravity, challenging us to keep exploring, keep questioning, and keep reaching for the stars.